Good morning, everyone. I'm really glad to be here. First of all, I must apologize for not being able to present this work in person. Edinburgh holds a very, very special place in my heart. I completed my PhD at the School of Geosciences here, and it would have been wonderful to return and share this research with you all face to face. Today, I'm going to talk about something that affects millions of smallholder farmers across Africa. Explore how do we balance things like pest pressure, natural pest control, and agriculture productivity in rapidly changing landscapes. This work is part of the broader Foster Health project, which is a collaboration between multiple organizations and universities across the UK, EU, and Africa. And I'm part of the work package 3, led by the University of Leeds, where I'm currently based, Wageningen University, and the University of Zambia. To give you a little bit of a context, Sub-Saharan Africa is facing a profound challenge. We need to feed a growing population while also protecting biodiversity and maintaining ecosystem resilience. And since 2000, the broader region has lost 10 to 15% forest or woodland cover. To remind, I'm using forest and woodland here interchangeably. This 10 to 15% decline has been driven primarily by charcoal production and agricultural expansion. What is particularly interesting in this trajectory is that initially or historically, it was a more natural or less human influenced forest or woodlands were converted into heterogeneous mosaic landscapes. And this is the most common type of a land cover that you'll see in Southern Africa. So a very heterogeneous mosaic landscape, which is a patchwork of woodland fragments, grasslands, and small agricultural plots. These are diverse, high beta diversity regions. These have already undergone, let's say, F to M transition. So these must have been woodlands before. These mosaics in some way represent a middle ground between, as I said earlier, less human influence or more natural habitat to more intensive agriculture, more cropland dominated landscapes that haven't happened yet in most of the Africa, but will happen in future. But now, driven by market demands and demands of commodity crops, for example, soya, there is an increased pressure. Majority of these mosaics are now being converted to and replaced by monoculture croplands. There's dominance of maize, and this maize is in many landscapes transitioning to soya. And this raises a very critical question that my research is trying to address. If we convert woodland or these heterogeneous mosaic to more commodity driven homogeneous croplands, or also transition from, let's say, more maize based farming to more soya, so maize to soya transformation, what do we gain and what do we lose? And what happens to the invertebrate communities or biodiversity that provides essential ecosystem services like that of pest control or pollination or nutrient recycling? This is the broader question that we are trying to explore. And this takes me to the study area in Zambia. We conducted this research in Chibombo district in central Zambia. This area is primarily characterized by the classic Miombo woodland, dominated by Brachystegia and Julbernardia tree species. These iconic African woodlands that many of you will probably be familiar with. Chibombo has undergone dramatic transformation since 2000. The woodland cover declined by 32%, cropland expanded by 56%, and this probably makes it a very ideal landscape to explore questions around comparing past, present, and future in terms of landscape. For example, let's say if a more continuous, less fragmented woodland was the past, and mosaic is the present, and more intense, homogeneous, cropland dominated landscape is the future. So we have all of these landscapes present in Chibombo, of course, to different levels and in different proportions, but still we can pick these landscapes and compare, and maybe from that try to understand or project what might be the implications if there is a shift from, let's say, woodland or mosaic to homogeneous landscapes. And just to add more context, most of the farmers are still small scale. Of course, there are some large scale farmers as well. Our focus of this study was small scale farmers who own 2 to 5 hectares of land. These are the farmers who grow several things, mainly maize, maybe some legume, mixed with vegetables. Some farmers in this community are also transitioning to soya monocultures. And this situation or trajectory is typical of much of Southern Africa. So our findings from Zambia-based case study can also have implications for broader Southern Africa. And you can get a sense of what this study area feels like. So you can see diversity of landscapes we are working with, from intact woodland or recent cleared woodland on top of the left side panel to more mixed mosaic field, which is the bottom left panel, to more cleared field with still some patches of vegetation left, and then bottom right, where in the distance there's a woodland being cleared. And to basically explore our broader question, we devised a couple of research questions that were guiding our broader research. So our research addresses three interconnected questions. First, how does landscape composition, the amount of forest, grassland, and cropland shape invertebrate community structure across different functional groups? Second, and this is crucial, do natural enemies like predators and parasitoids respond differently than pests to land use change? If predators are more sensitive to habitat loss than pests, we would expect that pest pressure to increase as landscapes become more simplified. And third, can landscape heterogeneity buffer pest pressures while maintaining ecosystem services? In other words, is there a sweet spot where farmers can be productive while also maintaining biodiversity and benefiting from natural pest control? And to explore these questions, we basically worked across 60 fields, 20 each in woodland, grassland, and cropland habitats. We conducted invertebrate sampling in both wet and dry seasons using pitfall traps for ground-dwelling invertebrates, pan traps for flying insects, and sticky traps for aerial insects. Alongside the sampling invertebrates, we also conducted farmer questionnaires to understand their perspectives on pest pressure and management practices. We also assessed direct crop damage on crops and compared with observed invertebrate abundances. We also did landscape characterization using sentinel imagery, also ALOS pulsar, to basically derive all the landscape and land cover variables. And we did this categorization at 1 kilometer grid scale to identify the landscapes, but also at the 250-meter scale to identify the spatial configuration and context around the field. And then critically, we also grouped all the invertebrates that we sampled into functional groups based on their ecological roles. For example, pests that damage crops, predators that suppress pests, pollinators that enhance yields, and decomposers that recycle nutrients. And quickly jumping on to the results. So we found that forest area or woodland area has a strong positive effect on predator abundance and biomass. Basically, every additional hectare of forest increases overall predator abundance as well as volume. Likewise, patch richness, which is basically landscape heterogeneity, also increased predator to pest ratio, which basically means that more diverse landscapes don't just have more predators, they have relatively fewer pests compared to predators. And in stark contrast, the increase in crop area decreased the predator to pest ratio. So as cropland expands, we lose the predators that provide biological control. When we calculated the impact of converting forest to cropland, we found a 37% decline in predator abundance. So this is not a subtle effect. It basically means that woodland retention is non-negotiable for natural pest suppression. So without woodland habitat or forest habitats, basically farmers will lose their natural allies in pest management. And then coming to pests, the pest story is a mirror image of predator story. So crop area strongly increased pest specialist abundance, which means that species that specialize in being crop herbivores or damaging crops, those are selected in more simplified agricultural landscapes. And interestingly, increase in grasslands, so places where woodlands are converted to grasslands or even fallows are becoming grasslands, in these areas, pest volume increased, which means that the size of pests in these areas was significantly higher than pests in more crop dominated areas. Essentially, this means that the pest responses are more nuanced than simply habitat loss is equal to more pests. And more concerning, crop area directly increased crop damage intensity. This means that this is not just about increase in pest numbers, it directly translates into actual yield losses. When we calculated the impact of forest or mosaic to cropland conversion, we realized that pest volume increased by 44% in more cropland dominated landscapes. So the double whammy is clear. You lose predators and gain pests. And this will lead to increased pesticide dependency among farmers, which is a costly and often environmentally damaging coping strategy. Coming to other two remaining groups, pollinators responded most strongly to patch richness. So landscape heterogeneity increased pollinator volume. So they need diverse floral resources throughout the season, which heterogeneous landscapes provide. Interestingly, both forest area and crop area had negative effect on pollinator abundance. So basically, in more homogeneous extremes can be forest or woodland or cropland in a more homogeneous conditions, it is not good for pollinators. Pollinators require the mosaic, the heterogeneity of the landscape. And then decomposers showed the strongest response to grassy mosaic chain. So basically, when these mosaic areas are increased, it mostly favors decomposers more than predators or pollinators. And these decomposers are crucial for nutrient cycling and soil health. And in these mosaics, there is also increase of decomposer turnover, which suggests higher functional diversity. And also, above ground biomass had a positive effect on some of the decomposer groups, showing importance of organic matter inputs. Just to summarize, predators need forest, woodland amount, and patch richness, which support larger bodied predators and pollinators. And these are often specialist species that require stable habitat. Pest species are sensitive to croplands. They are smaller, disturbance tolerant generalists that thrive when we simplify landscapes. Pollinators need heterogeneity. They benefit from diverse landscapes. Decomposers thrive in grassy mosaics where organic matter accumulates and creates favorable microhabitats. So the overall pattern is clear. Cropland expansion selectively favors smaller, disturbance-tolerant pests and decomposers, leading to a community-wide downsizing. We lose large-bodied specialists that provide critical ecosystem services when we move from woodland to mosaic to croplands. So this brings me to perhaps the most important observation or insight, which I call the Mosaic Buffer Effect. So we can model three scenarios to project what happens when different land use trajectories are happening. Scenario A represents the most common historical pattern: forest or woodland converting to grassy mosaic that I mentioned earlier. So this scenario shows biodiversity trade-off that is reversible and manageable. So if we maintain some spatial heterogeneity, some beta diversity, which enables a meta community source sync dynamics, the biodiversity loss happens when we go from woodland to mosaic, but that biodiversity loss is still manageable. And in fact, in some cases, species diversity increases by 20%, and functional uniqueness also increases because in a more mosaic landscape, there are some species that are not found in woodland dominated landscape. So functional uniqueness also increases. And in addition to that, we also see some modest increase in pest volume, roughly by 25%. And also we see slight decline in predator abundances and but increase in pollinator volumes. So basically, woodland to mosaic is maybe not so good in terms of biocontrol because pests are increasing, predators are declining, but generally it is still better for biodiversity. It is still better for beta diversity. It is still better from the perspective of pollinators and decomposers. And also the net biocontrol, there is a loss of about 10%. So there is decline, but it is manageable. And then scenario B is what is happening in most of the landscapes right now. So scenario B is shift from mosaic to monocultures. This shift causes trade-offs that strongly favor pests and a trade-off strongly against biodiversity. And here in this scenario B, which is mosaic to cropland transformation, species diversity collapses by 8%, functional uniqueness drops by 18%, pest volume increases by 12%, and predator abundance crashes by 22%, and pollinator volume also declines by 18%. So net biocontrol drops by 30%. And this scenario we need to avoid. Now, in scenario C, where some woodlands or forest areas are directly converted to cropland, this is driven mainly by market pressures and large-scale agriculture expansion. This scenario leads to severe, irreversible losses and dramatically increased pesticide dependency. Species diversity plummets 15%, functional uniqueness slightly increases, but this is the wrong kind of uniqueness. It is dominated by pest specialists. Pest volume explodes by 44%. Predator abundance crashes by 37%, and pollinator volume drops by 12%, and net biocontrol collapses by 50%. And at this level of biocontrol loss, farmers have no choice but to rely heavily on pesticides, creating a vicious cycle of resistance, cost increases, and environmental degradation. So it is a absolute no-no scenario. To conclude, landscape heterogeneity matters profoundly. Maintaining mosaic landscapes provides a viable pathway for balancing agriculture productivity with ecosystem service provision. But direct forest to cropland or woodland to cropland conversion creates irreversible trade-offs that hurt both biodiversity as well as farmers. The policy implications are clear. We need landscape scale planning that maintains habitat heterogeneity, prioritizes woodland conservation, and supports farmers to managing pest pressures through ecological intensification rather than chemical inputs. So with this, I would conclude my presentation. So thank you very much for your attention. Please feel free to connect with me on the email ID that is shown on the slide. Happy to discuss this research further. Thank you.